So next, I want to introduce you to a very important idea. It was introduced by Dirac. It's called the Dirac, delta function, or just a delta function. And the Dirac delta function is a bit of a misnomer because it's not a function. Okay, so the Dirac delta function is what is known as a generalized function. It doesn't have any of the nice differentiability properties of a normal function. It's a generalized function, or it's also come to be known as distribution. Dirac just introduced this because he needed it. He was not really bothered by the mathematical niceties. After he introduced it, mathematicians went and started asking questions, oh, is this well defined? As a result, they developed the theory of distributions, okay? Okay, so how do I introduce this? So let's start with the Fourier series, okay? So this is a Fourier series. So if I have phi of x, some periodic function, I can express it as a sum over all n of Fourier coefficient Cn and some basis functions which are exponentials. It's 2 pi I n x over L. So the periodicity is L, right? L is the period. Now the question is, suppose I give you this function, how do you find Cn? Okay. Well, to find Cn, what we do is that we multiply both sides of this equation by 1 over L. That's for normalization. Phi of x is multiplied by e to the power minus 2 pi I. M is an index. It's a particular value of that index. Cn is summed over, so n is a dummy variable. And mx by L, so we multiply both sides by these factors. And on the right-hand side, we have as a result plus 2 pi I n minus m x over L. And then we integrate both sides over the period. It could be from 0 to L or minus L by 2 to plus L by 2. It's your choice. Doesn't matter. And on both sides. Okay. Now, we are interested in evaluating this integral. So in this integral, this is an integer, right? So let's call it big N. And let n be a non-zero integer first, okay? So n is an integer, but it's non-zero. Then we are interested in knowing what this integral is going to evaluate to. Okay, this integral. So e to the power 2 pi I n x over L. Okay? I think I made some mistake here. Just 1 second, okay? Okay, I think. Yeah, I think I made a mistake, but anyway, hopefully that won't in my notes, but that won't. Okay, so do people have any idea what this is going to be when we do this integration?
Zero.
Exactly. And that's because if you know, this guy has a real part and an imaginary part, right? The real part of this is just a cosine function, right? So if I have a cosine function, it looks something like this. And if this is the period of the cosine function, say L, then you know that this is going to give you positive area. This is going to give you positive area, but that is going to be equal to the negative area in magnitude from here, right? So if you integrate over all of this, you're going to get 0. On the other hand, similarly for the sine function, right? So this is going to be the positive contribution, and this is going to be equal a negative contribution. So when you do the sum, you basically find this to be the result, okay? So I'm not going to waste my time do the math, but you should do it for yourself. Okay, when is this non-zero? This is non-zero when the integrand is 1. In other words, when n is 0. Okay, so as a result, what we have is that, so there's a 1 over L here for it to be 1. We have the result that the integral of those basis function from minus 1 over L to plus 1 over L, sorry, minus L by 2 and to plus L by 2, e to the power 2 pi I m minus n x over L of d of x is delta mn. Okay? So this is where delta mn is the Kronecker delta. So Kronecker delta is defined to have 2 indices. They're integers, and it's 0. It's 1 if m is equals to n, 0 otherwise. Okay. So when m is equal to n, we see this guy is 0. So the integrand is just 1 over L is just 1. And when you integrate from minus L by 2 to plus L by 2, you get L, and that cancels this and gives you 1. If m is not equals to n, then by this argument, this becomes 0. And that's why we have the Kronecker delta. Is this clear? This is a very important result. This shows the orthogonality of the circular functions. Okay. Are there any questions about this? Okay, so if I use this on the right-hand side, what do I get? I get this following result. The left-hand side is 1 over L integral from minus L by 2 to plus L by 2 phi of x e to the power minus 2 pi I m x over L d of x. On the right-hand side, I have a sum over n, and then there's c of n and the Kronecker delta nm using this result. But because of the property of Kronecker delta, if I do this sum, all the terms will be 0 except the term where m is equal to n. So the only term that will survive is the term where n is equals to m. So I will have on the right-hand side C of m. And as a result, I have figured out the Fourier coefficient for my whatever periodic function. It's given by this expression, okay? Is this clear what we're doing here? We're extracting the Fourier coefficient. Okay. So let's put all of this in a little bit of a more formal language. So the most central property here is that if I define a basis function, so I can think of the space of periodic functions with period L as some kind of an infinite dimensional vector space where each of the basis vectors are given by these guys, ENs. And they're defined to be 1 over square root of L e to the power 2 pi I n x over L. So I can think of these as basis vectors. And so there are an infinite number of these. And let's define an inner product. The dot product is a definition of an inner product. And the inner product between two of these E's, say EM and EN, is defined to be the integral from minus L by 2 to plus L by 2. Take this guy and EM and take its complex conjugate times EN d of x, okay? Let's not forget that this is a function of x. Okay, so if I do this, then this thing is just nothing but the rewriting of the left-hand side here, okay? Therefore, we find that our inner product, EM, is given by delta MN, okay? Is this clear? And this is called this is called in an orthonormality condition. So the word orthonormality is a portmanteau word which consists of orthogonality and normalization and normal. Okay. So where have you seen this kind of conditions before? Can someone tell me?
In R to the n.
In R to the n, okay. Anyone else? What does n mean? Where have you seen such a condition before? Sorry. In your like first year, no less, as physics undergraduates. So think of three-dimensional vector space. Okay, so you have, this is the z-axis, this is the y-axis, and this is the x-axis. Okay, so do you remember that we have these things called unit vectors? We call them I hat, j hat, k hat. Okay, and I dot j is equal to 0. But so let me put hats here, but I dot I is 1, right? So, and then similarly, j dot k is also 0, and it's equal to k dot I. but this is equal to 1 is equal to j dot j, k dot k. So if I call x hat, say I hat, j hat, k hat, so x hat is an element of this set, then x hat, say I, then x hat I dot x hat j is 0 unless both of them are the same, right? So it should be ij, right? So these familiar expressions are nothing but expressing the fact that we have these basis vectors which are orthogonal and normalized. So here our vector space was 3-dimensional, but here we have a vector space which is infinite dimensional because m and n go from minus infinity to plus infinity, right? And integers. Okay, it's a countably infinite vector space. Its dimension is countably infinite. Okay, is this clear? I mean, I want to stress on this. I want to stop here. I want to take questions. This is a conceptual leap, which is very straightforward from finite dimension to infinite dimension, but there are some kinks which I need to make sure you understand. So it's similar, but there's a difference. The difference is that here, the inner product is that it's real. So we could have written this as x hat I, x hat j equal to delta ij. But in this case, x hat I and x hat j is equal to x hat j comma x hat I. However, the way that we are defining this inner product, we see that the first factor is taken complex conjugation because we are dealing with basis functions or basis vectors which are complex. So in this case, this is not going to be true in this case, except instead what we will have is that em comma en star is going to be given by en. Okay? Is this clear? Do we have any questions? I really want you to tell me that you guys are following or not following. Okay, otherwise I want to stop here and really discuss these issues.
Yes, I got it. Like, understood most of the stuff.
Okay, anyone else?
Sir, is it because the integrand, like when we take en and em's inner product, the integrand becomes en star em?
Exactly. So if you take the complex conjugate, these two guys switch places, right?
Yeah.
Yeah, that's why. Okay, so inner products in mathematics, also are usually defined to be like this. Okay, and if they're 0, then that means that em is 0. Okay, if if the norm is 0, that means it's a trivial function, and all of this is satisfied in this case. Okay. All right, so good. So we are talking about inner. We just formalized it a little bit, and we introduced the notion of inner product on on our Fourier space.